Bismillahirrahmanirrahim. Assalamu alaikum. Our today's lecture is about codes. In today's lecture, we are going to discuss what are codes, different types of codes, numerical codes and alphanumeric code and alphanumeric code. In numeric code, we are going to discuss decimal codes, and in alphanumeric codes we are going to discuss ASCII codes, and also we are going to discuss in today's lecture error detection codes. Code. What is a code? A code is basically a combination of bits which is used to represent digits, numbers, symbols, alphabetic character, or any other object, any other type of information is called code. So a code is basically a combination of bits. An n-bit code can represent a maximum of 2 raised to power n entities, characters, symbols, digits. So if we have 4-bit code, in 4-bit code we can represent up to 16 characters or symbols. In 8-bit code can represent 64 characters, and 8-bit codes represent 256 characters maximum. Types of codes. So we have decimal codes. The decimal code includes BCD, binary coded decimal. This is a 4-bit code. XS3 code. This is another 4-bit code. Error detection code, gray code, and alphanumeric code, ASCII code. Binary coded decimal, BCD code. Binary coded decimal is a way to express each of the decimal digit 0, 1, 2, 3, 4, 5, 6, 8, 9. These are all decimal digits. So BCD represents the decimal digit through their corresponding 4-bit binary. Means 0 is represented by the 4-bit binary of 0. 1 is represented by the 4-bit binary of 1. The 2 is represented in BCD by the 4-bit binary of 2, and 9 is represented by the 4-bit binary of 2. So BCD, this is straightforward. In BCD, each decimal digit is represented by their corresponding 4-bit binary. Decimal 0 is represented by 0, 0, 0, 4 zeros, 4-bit binary of 0. Decimal 1 is represented by binary 001, 4-bit binary of 1. Decimal 2 is represented by 0010, 4-bit binary of 2, and so on. There are only 10 code groups in BCD system. We have 10 decimal digits 0 through 9. So BCD contains 10 combinations. So it is very easy to convert between decimal and BCD. BCD is a weighted code. The weights of BCD are 8421. BCD have a number of types. So the type of BCD which represents these decimal digits 0 to 9 is called 8421 code. The 8421 are the weights of, this is the weight of first bit, this is the weight of second bit, this is the weight of 4-bit, and this is the weight of the 4th bit. So the BCD which represent 0 to 9 digits are also called 8421 code. That's why it is also called 8421 code. Decimal code. So these are decimal digits 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. These are the 10 decimal digits. This is BCD or 8421 code. So decimal 0 is represented by 4 zeros in binary in BCD. So this is the 4-bit BCD. This is the BCD of decimal digit 0. This is the BCD of decimal 1. and this is the BCD or 8421 code of 2. So 2 in BCD is represented by these 4 bits. This is a binary of 2. 9 is represented by the 4-bit binary of 9. So this is a BCD code of 9. So these are all BCD code. Keep in mind, BCD is a weighted code, and BCD is not a self-complementary code. So look, the complement of 0 0 0 0 is 1 1 1 4 ones. So it is not present in this BCD, in the BCD table. So that's why it is not self-complementary codes. This is another look. This is another example. 1. This is a BCD code of 1 or 8421 code of 1. So look, the complement of this will be 1 1 1 0. So it is not also present in this in all these BCD combinations. So BCD is not a self-complementary code. To make BCD self-complementary code, so we add 3. So it becomes XS3 code. So in XS3, if we add 3 to each BCD code, so we get XS3 code. So this is the XS3 code of 0 decimal 0. This is the XS3 code of 1. This is the XS3 code of 2. This is the XS3 code of 3. So look, if we add 3, the BCD of 3 plus 0 1 1 plus 1 1, we will get this code. So look, this is a self-complementary code. So look, the complement of this is 1 1 0 0. 1 1 0 1 1 0 0 is present, so the complement is present. The complement of this 0 1 1 1, and the complement of this is 1 0 0 0, so it is also present. This is also the complement of this number. So complement of each code is present in XS3 code. So XS3 code is a self-complementary code. This is another code. These are the weights 8 4 minus 2 minus 1 code. So look, 0 is represented this. Basically you have to represent a digit like 4. So resolve this 4 into the sum of the digits. So 4 can be represented by 0 plus 4 plus 0 minus 0 minus 0. So the third bit will be 1, and fourth bit will be 0, the second bit will be 0, and first bit will be 0. So it becomes 0 1 0 0. So 4 is represented by 0 1. To represent 9, so this bit should be equal to, look, this should be equal to 1. This bit should be equal to 1, so it becomes 12, and these two bits become 1 1. So to represent 9, this is 1, this is 1, this is 1, this is 1. So 8 plus 4 is 12, and minus 2 minus 1 is minus 3. So 12 minus 3 is 9. So 9 is represented in this code. So this is another self-complementary code. 8 4 minus 2 minus 1. These are the weights. So to find a weight, to find 8 4 minus 2 minus 1 code, so break these numbers in these weights. So you will get the corresponding which weight is present, put a 1 for that, which weight is not present, put a 0 for that. So you will get this code. This is another code, 2421 code. This is also a decimal code and self-complementary code. So suppose we want to represent 5. So 5 is 4 plus 1. So 4 bit is 1, this bit is 1, this bit in 1, and these are 0. So 0 1 0 1 is the 2421 code of 5. The code of 7, so look, 4 plus 2 plus 1. So you can 4 plus 2 plus 1, so 1 1 1, and this bit is 0. Or you can make this 1 and this one and this one. So 1 1 0 1 is also represent 7. So this is a 7. this is the code of 7. So these are different decimal codes. They all represent decimal digits. These are all 4-bit code. BCD is not a self-complementary code, it's a weighted code. These are all weighted codes. However, X is 3, 8, 4, minus 2, minus 1, 2, 4, 2, 1. These codes are self-complementary. These are self-complementary codes. Invalid code in BCD is a 4-bit code, and we have seen that n-bit code represent 2 raised to power n symbols. So the maximum number of symbols that can be represented by BCD is 16. So in the first 10 combination we used to represent decimal digits, and the remaining six combinations. These 6 combinations are invalid code. They do not represent any digits. That's why in BCD these 6 combinations are invalid in the 8421 BCD code. So 10 10 10 11, maybe it represents in other BCD codes some entities. However, in 8421 code these are invalid codes. These are 10 10 10 11 1100 1101 and 1110 1111. So these are all, they are called invalid codes in 8421 code. BCD to decimal conversion, it is very simple. Replace each decimal digit by its 4-bit BCD with 4-bit binary. So to represent this 3-5, to convert this 3-5 to BCD, so the BCD of this 5 is 0 1 0 1. So this is a 0 1 0 1. This is the BCD of 5, and 3. The BCD of 3 is 0 0 1 1. So convert this 3 to its BCD. Replace it by its 4-bit binary or BCD 0 0 1 1. So this is 35 in decimal, and this is the BCD code. This is the BCD code of 35. To represent 98 in decimal, so replace 8 by its 4-bit BCD by its BCD code. Replace 9 by its BCD code. So you will get this is what the BCD of 98 in decimal. The BCD of 170 is replaced by BCD code of 0. 7 is replaced by BCD code of 7 is replaced by BCD code of 7 0 1 1, and 1 is replaced by BCD of 1. So this number is replaced by this. So this is another example. So replace each decimal digit by its corresponding BCD code. So you will get the BCD for that number. These are the BCDs 8421 code 0 1 2 4, and then this is the code of 9, BCD code of 9, or 8421 code of 1001. BCD edition. How do we perform addition in BCD? So BCD is a numerical code and can be used in arithmetic operation. Addition is the most important operation because the other 3 operations, subtraction, multiplication, division, can be accomplished by the use of addition. Here is how to add 2 BCD numbers. Step 1. Add 2 BCD numbers using rules of binary addition. We have discussed binary addition, rules of binary addition, in which 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, and 1 plus 1 is 1 0. So use 2 BCDs are added using rules of binary addition. In step 2, if a 4-bit sum is equal to or less than 9, it is a valid BCD number. If a 4-bit sum is greater than 9, 2 conditions there. If a 4-bit sum is greater than 9, or if a carry out of the 4-bit group is generated, it is an invalid result. Add, then what we have to do, we add. If in these 2 cases we add 6, the BCD of 6 0 1 1 0 to the 4-bit sum in order to skip the 6 invalid state and return the code to add 4 to 1. If a carry results when 6 is added, simply add the carry to the next 4-bit group. So these are the steps. Follow this step in addition of two BCD numbers. These are some examples. Suppose add the following BCD number. This is a BCD of 3. This is a BCD of 4. So let add them. So we add them. So 1 plus 0 is 1. 1 plus 0 is 1. 0 plus 1 is 1, and 0 plus 0 is 0. So look, this is a valid BCD. This is a valid BCD in decimal. 3 plus 4 is equal to 7. So there is no need to add 6. So look at this. This is 2, 3. This is the BCD of 3. This is the BCD of 2. And this is the BCD of 5. This is the BCD of 1. So let add. So they are the sum is a valid BCD. So there is no need to add 6. BCD of 6. This is another example. So all these are valid BCDs. This is another example. These are the invalid code. So if sum generates some bits are generate these codes, so they are invalid. And what we have to do in this case, in these cases, we have to add 6. So 1 0 0. Let add this. This is the BCD of 9. This is the BCD of 8. So 1 0 0 1 and 0 1 0. So add it 1 0 1 and 1. So look, this is an invalid BCD. These are invalid codes. 1 1 0 1 1 1 0. This is an invalid code. So in this case, what we have to do, we have to add the BCD of 6 to skip these 6 invalid codes. So the BCD of 6 is 0 1 1 0. So add this is at 6 1 0 1 0. 1 plus 1 is 0 and 1 is carried. So 1 plus 1 is 0 and 1 is carried. So 1 is carried. No, the 4 group generated a carry, so it will be moved to the next group. So the sum is no, it becomes a valid BCD, and this becomes the BCD of 1 is 0 0 0 1. So 1 3. The sum is 1 3. So in decimal, 9 plus 4 is equal to 1 3 in decimal, 13 in decimal. So this is another example. So 9, this is a BCD of 9, this is a BCD of 9. When we add it, so we get this a carry is, in this case, a carry is generated from these 4 bits. So here we got an invalid code, and here we got a carry from the sum of these 4 bits. So in these two cases, in this case as well as in this case, when we got a carry, so what we do, we add 6. So BCD of 6. So add 6 0 1 1 0. So it becomes 1 0 0 0 and 0. 1 plus 1 is 1 0. So 1 is carried. 1 plus 1 is 1 v 1, and this carry. So we put make it a 4-bit by padding 3 zeros on the left. 0 0 1. So it becomes 1 8. So these are how do we add BCD. This is another example. So look, when we add BCD of this is 1, this is 6, this is BCD of 16 to BCD of 15, 1, this is 1, and this is BCD of 5. So when we add it, so in this case a carry is not generated. However, this 1011 is an invalid code. So in invalid code, we add, what we do, we add 6, BCD of 6. So the BCD of 6, when we add it, we get this results. 1 plus 0, 1 plus 1 is 0, or 0 plus 1 is carried. So 1 plus 1 is 0 1 0, and 1 is carried 0, and the 1 is carried. So look, 1 will be put 1 will be here. This is a valid BCD. So when we put 1, so 1 plus 0 is 1, and 1 is down here, and 0 0. So this is a valid BCD. So if we add 2 BCDs and the result is greater than 9, so what we do, we add 6, BCD of 6. So this is another example, the last example. this is BCD of 7, BCD of 6, so this is 67, this is BCD of 3, and this is BCD of 5. So add it. So this is an invalid code when we add these two. So this is again an invalid code 1011. So we add 6 here, we add 6 here, so we get 0 0, and again the carry is generated from these 4 groups. Carry is brought here, so it becomes 0 0 1 0, and a carry is generated from these 4 bits, so it becomes 0 0. So in this way we add 2 BCDs. XS3 code, as we have discussed earlier, BCD is not self-complementary code. XS3 code is self-complementary but unweighted code. BCD XS3 code is unweighted code. XS3 code is issued by adding 0 1 1 BCD of 3 to the BCD code for each decimal digit. Means to get code of 5. So we add 0 0 1 1 to the BCD of 5, and we get XS3 code for 5. The other self-complementary codes are 2 4 2 1 and add 4 minus 2 minus 1 code. So these are we have discussed these codes. So and these are weighted codes. These are weighted codes. However, XS3 is not a weighted code but self-complementary code. These two codes are weighted codes and self-complementary code. The error detection code. So the gray code is basically the error. This is unweighted code, and this is used for error detection. The gray code is unweighted and is not an arithmetic code. That is, there are no specific weights assigned to the bit positions. The important feature of the gray code is that it exhibits only one single bit change from one code word to the next in sequence. The single bit change characteristic of gray code minimize the chance for error. So that's why it is used mostly for error detection. This is decimal digits 0 1 2 3 decimal numbers up to 15, and this is the binary 4-bit binary of these digits, and this is the gray code. So if we look at the sequence, the code words, this is the code word for 0, this is the code word from of 1, decimal 1. So if we move from this code to this code, so look, there is a single bit change. This bit has only changed. When we move from this code to this code, so this code is only this bit is only changed in this sequence. So in this sequence, this bit has been changed. So only you will experience a single bit code when you move from one code sequence to the next code sequence. So all this code sequence contains a single bit change. Look at this sequence 1 1 0 1, and this sequence, so this bit has been changed. This only single bit has been changed. So it contains a single bit change. The sequences of gray code contains a single bit change. How to convert binary number to a gray code. So this is the procedure. The most significant bit, leftmost bit in the gray code, is the same as the corresponding MSB in the binary number. Going from left to right, at each adjacent pair of binary code bits to get the next gray code bit. Discard the carries. You have to discard the carries. So look, this is an example convert. This is a binary number and you want to convert it to gray code. So one, this is MSB and this bit is LSB. So MSB in binary is the MSB of gray code. So bring it down as it is. Now add this MSB to the next bit. So 1 plus 0. So the sum is 1. So put it, this is the next bit position 1. Now add this 0 to the next one. So 0 plus 1 is 1, and 1 plus 1, look, this is 1 plus 1 equal to 1 0. So 1 is carry and 0 is the sum. We have to discard the carry. So 1 is discarded and the sum bit is written over here. So this becomes 0, and 1 plus 0 again is equal to 1. So this is a binary number. The gray code is 1101. So this is the gray code of this binary number. So in this way we convert binary number to gray code. A gray code contains a single bit change, exhibits a single bit change when we move from one sequence to the next sequence. Gray to binary code conversion. How to convert a gray code to binary. So the most significant bit, this is the procedure. The most significant bit, leftmost bit in binary code is the same as corresponding bit in the gray code. So put it down as it is. So this bit and both gray code and binary code, they are the same. Add each binary code bit generated to the gray code with the bit in the next adjacent position. Discard carries. Look at this example, 11011 to binary. Now we are going to convert this number into binary. So this is a gray code bit, MSB bit. So this is also a binary. This is the binary bits, MSBs are the same. So put it down as it is. Now add this, the gray, to this bit. Now this is the binary bit. So add this to the next in gray code bit. So 1 plus 1 is 1 0. 1 is carry, so discard the carry and put a sum bit over here. So 1 plus 1 is equal to 0. The sum is 0. 0 plus 0. Now add this bit to the next in gray. So 0 plus 0 is 0, and 0 plus 1 is 1, and 1 plus 1 is 1 0. So again a carry is discarded and some bit is written over here. So this is how we convert gray into binary. The binary number is 1 0 0 1 0. So this is what an example of binary to gray, and these are example binary to gray and gray to binary conversions. Alphanumeric codes. Alphanumeric codes are codes that represent numbers and alphabetic characters. Most such code, however, also represent other characters such as symbols and various instructions necessary for conveying information. ASCII, American Standard Code for Information Interchange. ASCII. So keep in mind we have two versions of ASCII. One is standard ASCII and the other is extended ASCII. Standard ASCII is a 7-bit code, and in 7-bit code which represents 128 characters. Actually, ASCII, standard ASCII is an 8-bit code with MSB always 0. In standard ASCII, the MSB, the 8-bit is always 0. The 8-bit code is 00 through 7F in hexadecimal. The first 32 characters of ASCII, the first 32 ASCII characters are non-graphic commands, non-graphic characters. They are never printed or displayed and are used only for control purposes. Examples of non-printable characters, control characters, are null, line feed, start of text, and escape. These are some examples of non-printable characters. So the first 32 characters are non-printable characters. The other characters from 00 to in decimal from 0 to 31. The other characters are graphic symbols that can be printed or displayed and include letters of alphabet, lowercase and uppercase, the 10 decimal digit, punctuation signs, and other commonly used symbols. So the ASCII represent these codes. Extended ASCII. Extended ASCII is an 8-bit code which can represent 256 characters. 2 raised to power 8 is 256. 2 raised to power 7 is 128. So ASCII represent 128 character standard ASCII, and extended ASCII represent 256 character. The first 128 characters are standard ASCII characters from hexadecimal 00 to 7F. The first 28 characters, these are the codes of those 128 characters, start from 00 to 7F in hexadecimal. The last 128 characters are called extended ASCII characters. So this includes what the standard ASCII contains. The last 128 characters are called extended ASCII characters, represented from hexadecimal 80 to FF. These are hexadecimal numbers. These characters are grouped into the following general categories: foreign non-English alphabetic characters, foreign currency symbols, Greek letters, mathematical symbols, plus, minus, drawing characters, bar graphing characters and shading characters. So the extended ASCII characters categorized in these categories. So these are all about code. So again, a code is combination of bits which represent symbols, digits, characters, special characters, entities, objects in digital systems. An n-bit code represent 2 raised to power maximum of 2 raised to power n entities. Thank you very much.